Good morning. From Makerspace under electrical module, we are going to see about electrical installation tools and safety equipments. So this is an experiment one which will be covering you what are the electrical installation tools we use. Usually use combine player, nose player, this is an wire cutter or wire stripper, this is an neon line tester, and this is an screwdrivers with Phillips and minus heads, and we have insulation tapes with the different color codings respect to phase, neutral and earth lines, and we have a measuring equipments which is multimeter which can operate up to 750 volt AC and 1000 volt DC, and it can also measure up to 10 amps of current, and it has a resistance tester, continuity tester, and non-contact EMF tester, and also we will have an clamp meter, and this can measure both voltage and current, and it is a non-contact type, so we don't need to disconnect any circuits. We can clamp this and we can measure the current values. This will be very helpful in measuring the live systems, and we have protective devices like MCBs, so this will trip for the faulty currents, and it has a ratings. So you can see over here the ratings. We have a lot of different types of ratings. This is an C32, this will operate up to 32. It is a double pole MCB, so it will trip for the faulty currents. Okay, and we have fuses which is also very important in protection. So it has a lot of standard wire gauge. This is a 0.35 mm fuse wire. This is a copper fuse wire. So this will rated up to 6 amperes protection, and this is 1.12 mm, and this will go up to 16 amps fuse rating. So these are about electrical installation, and it has standards also, IEC 6090000. So this is used for cutting, crimping and twisting, and also it has an insulation in its holder handles. So it is used to protect us from the live systems, and all these electrical equipments are equipped with insulations. So these are rubber insulations and glass materials, and also this is with the wood. So this is for braking and other things which were very tight-end systems. So everything we should be with safety, and it should have a specific standards, and insulation standards should be maintained. Thank you. Hello, now we are going to look into the UPS connection. So this is a 12 volt battery. We have 32 batteries which are connected in series. We have taken one positive terminal output and two negative terminal output, one at the end, one at the middle, to get two output voltages. The total output voltage here is 384 volts. So this is a 20 kVA inverter. So this can operate up to 400 volt, maximum up to 500 volt at the peak. So now I am going to explain you the inverter connection, how the input will come in, how it will be rectified, and again how it will be inverted back to the load. I am giving you a short connection scheme now.
So this is an 20 kVA inverter. The schema is like this. Now you can see the 230 volt input is available, and it is feeding to batteries and also to the load. Okay, so where the first operation, this is an rectifying operation. The AC is rectified into DC. It is fed to the battery and also to the load. So before the load we have an inverter operation. So inverting operation, the DC is converted into AC, it is fed into the load, and we have this special bypass arrangement. When the inverter is getting serviced, we can bypass the supply to the load. Okay, so I will give you these schemes over here. So as I said, this is an 3 terminals coming out. One is positive, other two are 2 negatives, and it is fed into the inverter. And then this is an AC input supply. So this is RYB neutral, which is fed into the inverter as an input, RYB with neutral, and these two are AC output, and this is a ground for the inverter. So this is an positive phase and neutral to the load. So it is connected over here and it is fed into the load. Okay, it is fed into the load through this MCB. If I turn off this, the output will be stopped, and if I turn off this, the input AC supply to the inverter will be stopped. I am just explaining you. Now I am turning it off. Now the inverter is in charging mode. I have turned it off. Can you able to see the beep? Now you can see there is no AC supply, 0 volt, 0 hertz, but the load is discharged through batteries. Thank you.
In module 4, today we are going to look into connection of DC machine and its speed control. So basically this is an rectifier unit. This will convert AC into DC. So we convert this into 264 volt DC and it is fed into the DC panels. This DC panel has a control MCBs and a main control switch. Once you do, this is a turn on position and this is a turn on position. Now it is given to DC bus and DC bus is giving supply to all these MCBs. We are going to operate in DC1 first bay, so we need to turn on this mask motor. So this is a bed 1 and now it has a DC control switch over here. So once you turn on, the DC supply will be fed into the bus. Now you can see the DC supply is available. We have an inbuilt digital voltage sensor and its display unit. It is to 11 volt available now, and basically DC machine has an armature and field windings. So the terminals are all available over here, and these terminals have been bought over here. That is armature first and armature second terminal, F1 and F2 terminals. This is a 3-point starter, L, A and F, which is a load terminal line. This is an armature and this is an field terminals. Okay. Now we are going to have a speed control of this through an field control method. We are going to give an resistance through this rheostat into the field winding. Okay. By the way, we are going to control the speed. Okay. I will just explain you the connections. So these are two terminals available now, and we have a safety MCB here also available. Once it is turned off, the supply will not be available here. If you turn on, supply will be available over this point. As of now, until I explain turn off. So this is a plus and this is a minus terminal. So the positive terminal is taken to the line to the starter, and from the starter A and F points are available. So A is an armature point. I am taken to the motor armature winding, and the field winding I need to feed to the motor field, but before that I include this rheostat. This is a minimum resistance position. This is a 360 ohm 1.5 ampere capacity rheostat, and I have connected to this point, and the output is taken at this point, and it is connected to the field winding, and armature and field other terminals are connected with the negative terminal of the supply. So the circuit is closed now. I am going to energize. Now it is energized. The supply is available in the starter point. Okay. So this is a DC starter. You should slowly start this. You can see the variation of speed. With increase in position, now if you leave this point, once it is reaching here, if I leave, it will not come back. Okay. Now you can see it is running at 1342. The speed has been measured with proximity sensor over here. The proximity sensor senses the speed. Okay. Now I am going to increase speed of this. So ensure you hold in this right position, the bottom, and you move through this. You do not touch any live parts. Okay. So I am standing on the mat. Okay. We should be standing on the mat. We should use an proper tool. So now I am increasing the resistance, and you can see the changes in the speed of the motor. With increase in resistance, I increase the current to the field so that I can increase in the speed of the motor. I can increase up to 1500 rpm, which is a rated rpm, and if I want to reduce, I can reduce the speed. Thank you.